A ladder with a length of 26 feet is propped against a wall that is perpendicular to the ground. If the top of the ladder slides down the wall at the rate of 5 feet per second, at the instant the top of the ladder is at the height of 24 feet, find the rate at which the A, base of the ladder, slides away from the wall, B, angle that the ladder makes with the ground changes, and C, angle that the ladder makes with the wall changes. We have a triangle here formed by the ladder propped against the wall, which is perpendicular to the ground. The length of the ladder is a constant, so we can label it as a constant on the picture, 26 feet. The top of the ladder is sliding down the wall, so there's no question that the height of that ladder is changing, so that side of the triangle is not a constant. We can label that as a variable of some sort. I will call it y. And we have a rate at which that's sliding down. Y prime, or dy dt, is given as a rate of 5 feet per second. However, y is decreasing in length as that top moves downward. Y is going to become a smaller length. So the rate is a negative 5 feet per second. And we want to look at the instant the top of the ladder is at the height of 24 feet. That will be the y is 24 feet. Now there's the third side of the triangle, and as the top of the ladder moves down the wall and the ladder does not change its length at all, the bottom of the ladder has to slide away from the wall. So this other side of the triangle, labeled as x, will also change. For part A, we want to find the rate at which the base of the ladder slides away from the wall. So we are looking for x prime. To find x prime, the rate of x, we need to relate it to the rate that we know, which is y prime. We have to relate x and y to each other. Well, x and y are legs of a right triangle, so we have the Pythagorean theorem here. And one leg squared plus the other leg squared will equal to the hypotenuse squared. There's our related variables equation. We can find the related rates equation by taking the time derivative of both sides, indicated by a prime on both sides. This will be a time derivative, and every variable is implicit with time, so every variable will get a prime when you take the derivative. So the first term on the left will be a power rule. Bring down the power, subtract 1 from it, leave the inside alone, but then multiply by the derivative of the inside, and that will give us an x prime for the derivative of the inside of the power, which was x. Derivative of x will be x prime. For the second term, we bring down the power, we subtract 1 from it, and we multiply by the derivative of the inside, which will give us a y prime. On the right, we have a constant, 26 squared. It's just a number of some sort. The derivative of that will be a 0. Since we're equal to 0, we can divide both sides by 2. The 2's cancel. We're trying to solve for x prime here. We need an x, a y, and a y prime. Now we have a y and a y prime, but we do not yet have an x value. However, we have a relation between y and x, so if you know one, you can find the other in the related variables equation. Let's plug a 24 in for y. I'm going to work that out down here near the picture. So we have the equation x squared plus y squared equals 26 squared. We can plug a 24 in for y. And now we can square these out. It turns out that 24 squared is 576, and 26 squared is 676. Now we can subtract 576 from both sides, and we end up with x squared equals to 100. And now we can take the square root, and that gives us x equals positive or negative 10, but we only want to keep the positive since x is supposed to be a measurement of the distance of the base of the ladder from the wall. We're in length units in this problem of feet, so this will be 10 feet. There's our x value, and that can now plug up in the related rates that we have in part A. 10 times the unknown x prime plus 24 times y prime, which is a negative 5, equals to 0. So we have 10 x prime, 24 times a negative 5 will be a negative 120. We can now add 120 to both sides, so 10x prime equals to 120, and we can divide both sides by 10, so x prime equals 12. X prime, or dx dt, equals to 12, and then the units will be the units of x, which is a length, which is in feet in this problem, over dt, which is time, which is in seconds units for this problem. So 12 feet per second. It's positive, indicating that x is becoming longer, so the bottom of the ladder is sliding away from the wall. For part B, we want to find the rate at which the angle that the ladder makes with the ground changes. Let's give that angle a name on the picture. This is the angle that the ladder makes with the ground. I will call it theta. We can use any trig function we want here that relates any of the three sides, though it's best to use the constant as at least one of the sides. The constant is the hypotenuse of the triangle. That's the 26 feet. And therefore we can use either x or y together with that hypotenuse. Perhaps we'll use maybe sine of theta here. Sine of theta, according to the triangle, equals the opposite side, which is y, divided by the hypotenuse, which is 26. We know the rate for y, and therefore we have theta now related to y in a related variables equation, and we can take the time derivative of both sides to get the related rates equation. We could also have used cosine of theta, and that would relate to x over 26. That would also work out. We will now generate the related rates formula by taking the time derivative of both sides, indicated by a prime on both sides. On the left side, the derivative of sine of theta is cosine of theta times the derivative of the inside, which will be theta prime. To complete the chain rule, every variable is implicit with time, and we'll have a prime in the derivative. On the right side, we have a variable y over a constant. Therefore, we don't need to use the quotient rule. The constant in the denominator will just come along with the derivative of the numerator. The derivative of y is 1, but then times y prime to complete the chain rule over that 26. We can now plug numbers in. The cosine of theta can be found from the triangle. According to the triangle, the cosine of theta is the adjacent side, which is x, and we have a measurement for x. It's a 10 feet we found here. And then over the hypotenuse, which is 26 feet. So the cosine of theta is just 10 divided by 26. Times the theta prime equals to y prime, which is a negative 5, over 26. We can multiply both sides by 26, which means the 26's will cancel because they're in the same position. They're both in the denominator on opposite sides of the equal sign. To simplify the algebra needed here, and now we can divide both sides by 10, so we end up with negative 5 over 10. 5 and 10 are both divisible by 5, so this will reduce to a negative 1/2. So theta prime, or d theta dt, will equal a negative 1/2 units of angle radians over time. In this problem, time is in seconds, radians per second. For part C, we want to find the rate at which the angle that the ladder makes with the wall changes. Let's give that a name in the picture. I will call that phi. One way to handle the rate of phi is to write a trig function for phi using either x or y together with maybe the hypotenuse of 26. That would work out. But a simpler way to handle it, now that we have theta prime in part B, is to relate theta and phi to each other, because a triangle has its angles add up to be 180 degrees. And we have theta, and we have phi, and we have the third angle, which is the 90-degree angle, and all of that should total up to 180 degrees. We can now subtract 90 from both sides, and we get theta plus phi equals to 90. There's our related variables equation. We can take the time derivative of both sides of that equation, indicated by a prime on both sides. Theta plus phi prime equals 90 degrees prime. On the left side, the derivative of the first term, theta, will be a 1 times theta prime, so theta prime, plus the derivative of the second term will be 1 times phi prime, so phi prime, equals the derivative of 90 degrees, which is a constant. The derivative of a constant is 0. We can now plug our numbers in. We have a theta prime from part B. It's a negative 1/2, plus the phi prime equals to 0. And we can now solve for the phi prime by adding 1/2 to both sides. And that gives us phi prime equals to a positive 1/2. So phi prime, which equals to d phi dt, will equal to a positive 1/2. Again, the units will be an angle of radians over time of seconds. Theta prime was a negative, so theta apparently was decreasing this problem. Phi prime was positive, so phi was apparently increasing in this problem.